All right, welcome back. On to 3.5, least common multiple. So this textbook teaches least common multiple in a slightly different way than how I learned it. I think it's hard to remember how I learned it, but I actually think it's a really neat way of computing these. So I think this is actually kind of a fun section. So I don't know if you'll agree or not. Let me know in the comments if you think this is a pretty neat section. So jumping into it, a least common multiple, what does that mean? So first of all, we talked about multiples in 3.1. If you need a refresher, go ahead and check out that section. But basically a multiple is, for example, multiples of 3 would be 3, 6, 9, 12. Also, negative 24, for example, would be a multiple of 3. If you can multiply some integer, whether it be positive or negative, times your number, it would be the product of that. So if you can get a product starting from whatever number you're trying to find a multiple for, 3 in this example, then it would be a multiple. So it's a common multiple. So if you have two different numbers, let's say you have numbers 3 and 5, and you have multiples of 5, which are 5, 10, 15, 20, and so on. What is a common multiple? What's a multiple of both of those numbers, 3 and 5? Well, 15, is one example that is a multiple of 3 and is a multiple of 5. 30 is another example. It's a multiple of 5 and is also a multiple of 3. So those are common multiples. The least common multiple would be the smallest of those positive multiples. So if we have the integers 2 and 3, we know that the multiples of both of those, the common multiples, would be 6, 12, 18, 24, and so on. But what's the least common multiple? Well, that would be 6. Now let me get my pen. The smallest of those common multiples would be 6. All right, so let's go ahead and see how we can compute these. So first of all, we're going to start off by listing the 5 smallest positive multiples of 18. So we have 18, we have 36, 54. Also, side note, as I write these, I'm going to stop saying pause this and try it on your own. Still feel free to try these on your own. If you read the question, you think it's something that you might be able to do on your own, go for it. But as we get further into this course, we're going to come across more and more things that are going to be new to you. And because some of these are going to be new to you, you might need to watch me go through it first to see how to go about doing it before trying it on your own. But if you think that you can do it, go ahead and try it. But I'm not going to be saying pause this and try it on your own anymore. I'm going to go ahead and just show how to do some of these. So multiples of 24 are going to be 24, 48, 72, 96, and 120. Okay, so those are the 5 smallest positive multiples of 24. Now, what are the 3 smallest positive common multiples of 18 and 24? Okay, so common multiples, 18, no. 36, no. 54, no. 72, yes, that is a common multiple. Okay, and I don't see any other ones here, so we might need to continue getting some more multiples here. So after 90, we'd have 108. We have 126, 144, 162, 180, 198, 216, and we'll stop there for now. And for 24, after 120, we have 144. Ding, 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 we got another one. 168, 192, and 216, ding, ding, ding. So we'll stop there because we have 144 here. And we have 216. So that's the first 3 multiples, or common multiples of 18 and 24. So what's the least common multiple? Well, it's the smallest one, it's 72. 72 is the least common multiple of 18 and 24. Okay, this is a weird, how are the common multiples you found in part C related to the least common multiple? Well, it's just the smallest one, right? Okay, so this is a way to find common multiples. Something that, one note also, is something that will always be a common multiple is if you multiply these together. 18 times 24, of course, will be a multiple of 18, and it will be a multiple of 24. So if you just want to find a common multiple for some problem that you're doing in the future, that's a way to do it easily. You always know that multiplying them together would be a common multiple, but not necessarily the least common multiple. Sometimes it is, but it's not always the least common multiple. All right, so let's find the prime factorizations of the 5 smallest positive multiples of 18. So again, that was 18, 36, 54, 72, and 90. Okay, so the prime factorizations. So let's see, prime factorization of 18 would be, let's see, 9 and 2. And that'd be 3 and 3. So the prime factorization here would be 2 times 3 squared. Okay, that's cool. So how about 36? Let's do 36. And then we have 2 times 18. Well, we already know that 18 is going to be 2 times 3 squared. So this is just 2 times 3 squared. All right, does that make sense? Because we have this prime here. I know it's covered up by these words. Sorry about that. We have this 2 here, but then we have just the prime factorization of 18. We just got that one. So it's 2 times the prime factorization of 18. So just an extra 2, right? So 2 squared times 3 squared. So 54 is going to be 54. Well, we know this is the third multiple of 18, right? So this is 18 times 1, 18 times 2, 18 times 3. So this is just 3 times 18. So we know that this is going to be 3 times 2 times 3 squared. So that'll be 2 times 3 and an extra 3 cubed. This one here is going to be 4 times 2 times 3 squared. But 4 is not a prime. So let's go ahead and rewrite this. The prime factorization of 4 would be 2 squared, right? So 2 squared times 2 times 3 squared. Now we combine our 2's, and we have 2 cubed times 3 squared. Okay, and lastly we have 5 times 2 times 3 squared. And we don't have a 5 here, so we'll just go ahead and tack that on the end. So 2 times 3 squared times 5. So those are our prime factorizations. So do you notice anything interesting about these prime factorizations? Well, I mean, we kind of showed it here, that they all have this 2 times 3 squared in there. They just have some extra integers, an extra prime factorization tacked onto that, but they all are multiples of 18. We know that, so that means they're all going to contain 18 somewhere in that prime factorization. Okay, can we use that? The prime factorization of 72 is 2 cubed times 3 squared. So using the given prime factorization of each of the number below, determine if the number is a multiple of 72. Okay, so just like we knew from 18, if we see 2 cubed times 3 squared within this number, we can say that it is a multiple of 72. So we have 2 to the 5th here, and 72 needs 2 cubed. So let's pull out a 2 cubed. So 2 cubed times, well, we need to get back to 2 to the 5th, so we need 2 more. Remember our exponent rules. So if we have the same base, we multiply them together, then we can add the bases. So it'd be 3 plus 2 would be 5. All right, so then that's what we want. So can we pull out 3 squared out of this? Sure. So let's do 3 squared. And this is 3 cubed, so we'll multiply another 3, or 3 to the 1. And so now we know that multiplication is commutative, so we can change the order. So let's do a squiggly line. Let's do 2 cubed times 3 squared. 3 squared times, what else do we have left? We got 2 cubed. We need another 2 squared. and another 3 to the 1. Okay, so the reason why I did it this way is if we do this, parentheses don't really mean anything here, but just wanted to kind of show that, look at this. That is 72. So now we have 72 times 2 squared times 3, which would be 72 times 2 times 2 would be 4, times 3 would be 12. So 72 times 12 would be 864, which means 864 is a multiple of 72. Okay, so this next one here. So we have 2 to the 4th. Let's go ahead and pull out a 2 cubed. So 2 cubed times another 2. So we can get back to 2 to the 4th, right? So then we need to pull out a 3 squared. All right, so can we pull out a 3 squared out of this? So 3 squared would be 9. Can we pull out a 9 anywhere? I don't think we can. There's no 3s, no bases of 3s here. So I don't think we can. Is there any other way to do it? Is there any other possible way? Well, one thing we didn't really talk about in the last section is, are there any other prime factorizations of 72? So if we have 72 and we want to do the prime factorization, so 72 is 2 times 36. 36 would be 6 times 6, which would be 3 times 2 and 3 times 2. Which would be, we'd have 1, 2, 3 2's, 2 cubed times 3 squared. Yeah, it's the same prime factorization we got here. Is there any other way to get to 72? Maybe something like, I don't know, I'm making something up, 5 squared times 7 or something like that. This isn't it. This would be 25 times 7. That would be too much. But the point is there any other prime factorization so that maybe we can just like do something different to get to 72, and then maybe we could match here on 400? The answer is no. There is no other prime factorization. There's only one unique prime factorization for every integer, which means there isn't any other way to prime factorize 72. So there's no way that we can like just use a 5 instead of some combination of 2's and 3's. There is no other way to do it, which means that there is no way to extract a 72 from 400. So that means it is not a multiple of 72. We can also do this by doing 400 divided by 72 and realize that there's going to be a remainder there to know that it is indeed not a multiple of 72. But this one here is. All right, so how about 1008? So let's go ahead and pull out a 2 cubed. So 2 cubed times 2 to the 4th. So we need another 2 to the 1 to make 2 to the 4th. Okay, how about 3 squared? Can we pull out a 3 squared? 3 squared. Yeah, that's just all of it, so that's fine. And that's it. And then we have to remember to keep our 1008 intact by adding on this 7 to the 1. Okay, so let's go ahead and use our commutative property and rearrange. So we have 2 cubed times 3 squared. Right, that's our 72, and what's left? So we got 2 cubed and 3 squared, so we have 2 times 7 that's left. So this would equal 72 times 14. Okay, so this is indeed a multiple of 72. How about this one? So can we extract a 2 cubed from this? No, we cannot. So that is not a multiple of 72. All right, so suppose we have the prime factorizations of 2 positive integers, m and n. How can we use these prime factorizations to tell if m is a multiple of n? Well, we just did that. We need to be able to pull out the prime factorization from some other integer. Okay, so how can we use the prime factorizations of 24 and 90 to find LCM of 24 and 90? So this, the format of how this was written here, that's what's known as a function in programming. So if you think of a box, a computer, okay, you have a LCM computer. It's going to perform some functions. You're going to pass in some input. In this case, we're passing in the input of 24 and 90. We pass in that input, and then it's going to do something. We don't know what computers do sometimes. Sometimes we do, but sometimes we don't know what they actually do, but we do know that they're going to spit out some output. So we're just going to find out what is the output that it's going to spit out. So just get familiar with this, with how this is written. This is just called a function. And it's how you would tell a computer to compute something. All right, so prime factorizations of 24 and 90. Let's go ahead and find those out. So 24, let's get the prime factorization for that. It's going to be 6 times 4. Actually, let's do, let's do 6 times 4. That's fine. 3 times 2, and 2 times 2. Okay, so prime factorization is going to be 2 cubed times 3. How about 90? So 90, I'll write it here. It's going to be 10 times 9. 5 times 2, and 3 squared, or 3 times 3. So prime factorization for 90 would be 2 times 3 squared times 5. Okay, so use the prime factorization of 2490 to find the least common multiple. Okay, so in order for it to be a multiple of 90, let's go one base at a time. So let's look at the bases of 2. In order for it to be a multiple of 90, we need at least 1 2. But to be a multiple of 24, we need 3 2s. So if it's going to be a multiple of both of them, then it has to be at least 2 cubed in there, right? Because 2 cubed works for 90 because it has at least one of the 2s. But if we had anything less than 2 cubed, it would not be a multiple of 24. So we have to have at least 2 cubed. How about 3s? Same things goes with 3s. So we could make 24 with only 1 3, but we can't make 90. We have to have at least 2 3s. So this has to be at least 3 squared. So we want to take that highest exponent of each base. So 5, there is no 5 in 24, but we do need a 5 for 90. So we'll always need a 5 for a common multiple. All right, so what does this come out to be? 2 cubed is 8. 3 squared is 9 times 5. 8 times 9 would be 72 times 5. And that would end up being, if you multiplied that out, you would get 360. And 360 would be the least common multiple of 24 and 90. Okay, we'll use that same strategy to compute these least common multiples. If you want to give these a shot on your own, you should have enough information now to be able to do these, but I'll go ahead and go through these. So if we do the prime factorization for 96, let's see, 96 would be, so 45 times 2 would be, where was I? Would be 90. So what did I say? 45, 46, 47, 48 times 2 would be 96. Let's see. If we cut 48 in half, then we would get 24. And then we would do 6 times 4, 2 times 2, and 3 times 2. So it looks like prime factorization for 96 would be 1, 2, 3, 4, 5 2s. So 2 to the 5th times, and then 1, 3. So times 3. Okay. Prime factorization for 144. 144 would be, let's do 12 times 12. And we'll do 6 times 2 and 3 times 2. You know this side's going to be the same, so we're going to have just double the amount of these primes. So we have 2 2s here, so we know it's going to be 2 to the 4th. And we have 1 3, that's going to end up being, oops, times 3 squared. Okay, so to find the least common multiple, we need at least 5 2s, so we need 2 to the 5th, times, we need at least 2 3s, so 3 squared. And that's going to be 2 to the 5th would be, let's see, 2 times 2 is 4, times 2 is 8, 16, 32. So it'd be 32 times 9. 32 times 9 would be 270 plus 18. 270 plus 18 would be 288. All right. So 28 and 35. So I'll just go ahead and write out the prime factorization. You can go through the prime factorization if you want to, but to save some time, I will let you know that the prime factorization for 28 is going to be 2 squared times 7. Prime factorization for 35 will be 5 times 7. Okay, so the prime factorization, or the least common multiple here, would end up being, we need 2 2's, so 2 squared times 5 times 7. Because we only have 2 squared in one of them, so got to take that, and we only have 5 in 35, but we need both of those. We need the 2 squared, we need the 5, and they both have a 7, so we'll use that 7. And then that will give us, if we multiplied this out, would end up being 140. All right, so least common multiple for, these are already prime factorized, which makes it a little bit easier for us, I think. So we need at least 2 2's, so we have 2 squared. We need 3 3's, they both have 3 3's, that works out, 3 cubed. We need at least 2 5's, 5 squared, and 1 7. And if we were to multiply all that out, we would get a big number, 18,900. Okay. And we could actually do that a little bit, not super easy, but in our head we could do 4 times 25 right here. 4 times 25 would be 100. 27 times 7 right here would be 189. Not super easy to do in your head, but we'd have 100 times 189, and that's how we get 18,900. All right, so then the least common multiple of 24, 36, and 42. All right, so if we have these prime factors, then we'd have 24 would be 2 cubed times 3. For 36, we would have 2 squared times 3 squared. And for 42, we would have 2 times 3 times 7. Okay, so for all of these, we need to get the largest of the same base. So the least common multiple would be, the largest 2 here we have is 2 cubed. How about the largest 3 here? We have 3 squared. And then what else do we have? And then a 7. Okay, so then we'd have 8 times 9 times 7, which would give us 504. All right, I'll just put some boxes around these so they're a little bit easier to see. Those are our least common multiples. Okay, so are the least common multiples of 2 times 500 and 2 times 300 and 2 times the least common multiple of 500 and 300 equal? Okay, so let's find out. First, let's go ahead and get the least common multiple of 500 and 300. So the prime factorization for 500 would be 2 squared times 5 cubed. And for 300, it would be 2 squared times 3 times 5 squared. So the LCM of 500 and 300 would be equal to, let's see, we have 2 squared, we have a 3, and we have 5 cubed. And that would be 4 times 3 times 125. So 125 times 2 would be 250. So times 4 would be 500. 500 times 3 would be 1,500. 1,500, okay? So now how do we compare that to this other one here? So we already know the prime factorization for 500, so 2 times 500 would just be another 2, right? So we'd have 2 cubed, so 1,000 would be 2 cubed times 5 cubed. And for 600, again, it's just 2 times the prime factorization we already have. So just adding in another 2 cubed, or multiplying in another 2 technically, but 3 times 5 squared. Okay, so then what would the prime factorization, or would the least common multiple of these two be? So we need a 2 cubed, and then we need a 3, and we need 5 cubed. And this would end up giving us 8 times 3 times 125. So we saw that 125 times 4 was 500. So 125 times 8 is 1,000. So this would end up being 3,000. So is 2 times each of the numbers the same thing as just doubling the LCM? And it is. Look, 1,500 and 3,000. 3,000 is just twice as much as 1,500. So would that always be the case? So would it always be the case that 2 times some A and 2 times some B, would that least common multiple be the same thing as twice the least common multiple of half of those? And it is true that that would be the case because of this. You're just adding in another factor of 2 for both of them. So when you find the least common multiple, the factor of 2 is just an extra 2, which means the least common multiple will always be doubled because of the extra factor of 2. So then C, same thing, but we have a factor of 15. Can you pull out that 15? And same thing like we did for here, we'd end up pulling out, instead of pulling out a 2, we'd pull out the prime factorization for 15, which would be a 2, 15 would be 3 times 5, right? 3 times 5 would be 15. That's a prime factorization. So we'd be pulling out a 3 times 5, and then whatever A and B is, we'd have an extra factor of 3 and an extra factor of 5 that would end up being for both of our integers. And so for the least common multiple, they would have to be in the least common multiple as well. So that 15 would have to be in the result of the least common multiple. So this also is true. So we can factor out common multiples. We can factor out of the least common multiple to make it easier to solve. And we can do that with this one right here. So if we were to try to find the prime factorization for these numbers, that would not be a very fun day. But we don't need to do that because we can see that this number and this number share a common factor. So 606060 would be the same as saying 6 times 101010. And this number here would be the same as 7 times 101010. And now we can factor this out. So now we can say 101010 times the LCM of 6 and 7. So now what's the least common multiple of 6 and 7? Well, let's see. 6 would be 3 times 2, or 2 times 3. I'll put them in the correct order. 2 times 3. And 7 is already a prime. So the least common multiple would be 2 times 3 times 7, which would be 6 times 7, which would be 42. And I mentioned a couple slides ago that sometimes the least common multiple would just be multiplying the two numbers together, and that is the case. The smallest multiple that these two numbers have in common is just multiplying them together. It's not the only common multiple they have, but this is the least common multiple. It's 42. So what is the least common multiple of this? Well, it's 42 times all that junk. So that's going to give us 42, 42, 42, and a 0. So this would be the least common multiple of those two numbers. So that would have been a challenge to solve if we didn't have this fact known that we could factor out this 10, 10, 10. All right, our favorite, also check this video out here because it gives you some nice tricks to calculate these least common multiples. All right, word problem, our favorite. Everyone loves word problems, right? A church rings its bell every 15 minutes, and the school rings its bells every 20 minutes. And the daycare rings its bell every 25 minutes. If they all ring their bells at noon on the same day, at what time will they next all ring their bells together? Okay, so we know that this is going to ring at, if it rang at noon, it's going to ring at noon, and then 12:15, 12:30, 12:45, 1, and so on, every 15 minutes, every multiple of 15, right? And the same thing for the school. It's going to ring at noon, and then 12:20, and then 12:40, and so on. And same for the daycare. It's going to ring at noon, and then 12:25, and then 12:50, and so on. So all the multiples of 25. So what's the next time they will all ring together? So we have to get the least common multiple of these three numbers, 15, 20, and 25, to see how many minutes it will be, the least number of minutes it will take for them all to ring at the same time once again. So let's go ahead and get the prime factorizations for these three numbers. So 15, the prime factorization would be 3 times 5. 20 would be 2 squared times 5. And 25, we should know this one, is 5 squared. Okay, so the least common multiple of these three would be, let's see, the smallest two, or the largest two would be 2 squared. It's also the only two. The largest 3 is also the only 3. And the largest 5 would be 5 squared. So looks like we have 4 times 3 times 25. 4 25s we know is 100. So 100 times 3 is 300. Okay, but we're not done yet. So what is this asking? If they all ring their bells at noon on the same day, at what time will they next all ring their bells together? So these are in minutes, right? 15 minutes, 20 minutes, and 25 minutes. So what is this number saying? What does 300 mean? 300 is a number of minutes. That is the next, that's how much time has to pass for them all to ring at the same time. It's 300 minutes. 300 mins, okay? So how does that help us out? So if they all rang their bells at noon, then we know that 300 minutes later, it's going to ring again. And every 300 minutes, they will all ring at the same time. So what time will it be 300 minutes after noon? Well, how many minutes are in an hour? 60. So what's 300 divided by 60? 300 divided by 60. We can cancel out one of these zeros. So what's 30 divided by 6? And we know that that is 5. And that's going to be converted to hours, right? So 5 hours after noon, they will all ring together. So what time will they ring together? 5 p.m. Okay, so the number 16,128 is a multiple of 6, 7, and 8. What is the smallest multiple of 6, 7, and 8 that is greater than 16,128? All right, this one is, it might be confusing and tricky to know how to get started. But just like I mentioned in last section, if you don't really know where to start, just start doing something. Start with doing what we've been doing. Let's go ahead and get prime factorizations for some numbers and see if we can find least common multiples and see where that leads us. So we know that this number is a multiple of 6, 7, and 8, but it's probably not the least common multiple, right? So maybe we should find the least common multiple. I don't know if we need it or not, but let's go ahead and find it and see if we can come up with an idea. So what's the prime factorization for 6? That's 2 times 3. 7 is just 7. 8 would be, say, 4 times 2, and that would be 2 cubed. So the least common multiple here would be, we need at least 3 2s. Oops. 2 cubed. And we need at least 1 3. And we need 1 7. So this would be 8 times 3 times 7. So let's see what that would be. 8 times 3 is 24 times 7. Let's do 24 times 7. We have 28. 7 times 20 is 140. So it looks like that would be 168. Okay, so the least common multiple would be 168. So how does that help us here? Well, we know that every 168, we're going to have a common multiple. So let's do some smaller numbers here to show something. So let's use the numbers 2 and 3. Okay, what are the common multiples of 2 and 3? So we know that, so the multiples of 2 would be 2, 4, 6, 8, 10, 12, and so on. And here we have 3, 6, 9, 12, and so on. So for common multiples, we have 6, we have 12, and then we know we'll have 18, 24, and so on. But we know that, so the least common multiple is, actually, you know what, just show something, I'm going to go a little bit further. So 14, 16, 18, 20, 22, 24, that might be enough to show this. So 12, 15, 18, 21, 24. Okay, so we have, the next one is going to be 18, and the next is going to be 24. So what do you notice about these jumps? They're 6 apart. Add 6 to 6 and you get 12. Another 6 is 18. Another 6 is 24, which means that every hop to the next common multiple will be adding the least common multiple. So if you find the least common multiple, after that, you know that every single next common multiple will just be adding another least common multiple. And so we know that 16,128 is a multiple of these 3 already. So we know that that is a common multiple. So 16,128. Well, what's the next common multiple going to be? Well, we know we can just add a 168. So let's see, that would be 16, that would be 9, 2, 6, 1. So it looks like we have 16,296 would be the next common multiple after 16,128. All right, so what's the smallest positive integer greater than 1 that leaves a remainder of 1 when divided by each of 6, 7, and 8? Well, we know in the last slide we found that the LCM of 6, 7, and 8 was 168. Okay, and for it to be a multiple of all 3 of these numbers, we know that it would divide evenly with no remainder. Right? So if we do 168 divided by 6, we would get 0 remainder. If we do 168 divided by 7, we get 0 remainder, and same with 8, because they're multiples of all 3, so they have to give us 0 remainder. So what would give us 1 remainder? Well, what would happen if we just added 1? And we said 169 divided by any of these numbers. So divided by 6, let's say. Well, if we know 168 would go in evenly, and what would that be? Just for fun, let's see. 16 would go into, or 6 would go into 16 2 times. So let's start with 20 and say 12. This would leave us with 49. So we know 48. 6 times 8 would be 48. And that would give us a remainder of 1, which is what we're looking for. So 28 times 6 was 168, right? 28 plus 6 is 168, which means 169 would be, it would go in 28 times with the remainder of 1. And the same thing would happen for 7. We're not going to go ahead and divide it all out, but it would be 7 times some whole number with 0 remainder to get to 168. So if we did 7 times whatever number that is to get 168, well, we know that would give us 168, and so that would give us a remainder of 1 if we were at 169. So the answer to this would be the smallest positive integer greater than 1 that leaves us a remainder of 1 when divided by each would be 169. Okay. So there are other numbers, by the way, I want to point this out. There are other numbers that would give us a remainder of 1 for each of these numbers. So let's say we have the number 7. Okay? If we did 7 divided by 6, that would give us a remainder of 1, right? But if we did 7 divided by 7, of course, that would not give us a remainder of 1. So if all 3 of these were to give us all three of these to give a remainder of 1 would have to be going 1 over a common multiple. And to get the smallest positive integer greater than 1, that leaves a remainder of 1. That would be 1 more than the least common multiple. There are other numbers that would give us a remainder of 1 that would be larger than 169, but it wants the smallest one. All right, find the smallest positive integer that leaves a remainder of 5 when divided by 6, 6 when divided by 7, and 7 when divided by 8. So it's kind of the reverse, right? It would be it'd be 1 less than being a whole number. So if 168 gave us a remainder of 0, going down to 167 would not quite get us to a multiple of 6, not quite get us to a multiple of 7, and not quite get us to a multiple of 8. It would be 1 less than all of them. If you wanted to test that out real quick, if we said 167 divided by, let's say, 8, this would go in 20 times to be 160. So it would leave us with 7, and that's the remainder. So a remainder of 7 when divided by 8 is exactly what we're looking for. And we'd find the same if we divide all 3 of them. So the answer for this one would be 167. And that's it. So that's 3.5. Go ahead and do these exercises. Hopefully this lesson wasn't too bad, and it was kind of neat how you can extract some prime factorizations from one number to another to find that they are multiples of each other. But anyways, go ahead and do these exercises, and I'll see you next time for 3.6, which I believe is, it is not the last section. We have 2 more sections, divisors and then greatest common factors. So I'll see you next time.